Right, let's start. Hello everyone, hope you're all well. Welcome to today's webinar, Heat Pump Solutions for Low Carbon Buildings. This is Gürcan Serdaroğlu from Energy Innovation and Collaboration Team at University of Nottingham. I will be the first speaker today and will give a brief information about heat pump technologies. I'm joined by Seamus Garvey, Professor of Dynamics at the University of Nottingham, the Director of the Rolls-Royce University Technology Center, and G-ERA Lead for Energy Research Accelerator, and Phil Hurley, Managing Director of NIBI Energy Systems, also Vice Chair of the Heat Pump Association. Seamus and Phil will talk about the role of heat pumps in achieving a net zero UK and what is required for them to gain market penetration. That will be 15 minutes. There will be 15 minutes question session at the end of the webinar. If you have any questions, just pop them in the chat box during or after the talks. We will try to answer as many questions as we can today, but if you don't get to your question during today's webinar, we will follow up later. The session will be recorded. We would appreciate if you keep your microphone muted and your camera off during the webinar, please.
Not everyone comes in on time, like me.
So this webinar has been organized by Energy Innovation and Collaboration Team. Before talking about the heat pumps, I just want to give a very brief information about our project Energy for Business and how we can help your business through this EU-funded support. Energy for Business project is established to forge links between the businesses and world-class academics, researchers, and graduate talent in the energy field. This low-carbon project is funded by the European Regional Development Fund to provide fully funded support to SME businesses, sole traders, and social enterprises in the Nottinghamshire and Derbyshire region until the end of September 2022. We provide a wide range of support, including organizing free events and workshops in low-carbon technologies. This is currently in webinar format due to the COVID-19 situation. We also offer student placements and knowledge of transfer partnerships. Grants are also available for energy improvements, which also cover the heat pump technologies. Finally, we offer specialist consultancy from world-class academics and access to outstanding research facilities. If you want to find out more about our support and potential collaboration opportunity with the University of Nottingham, please get in touch. We welcome the opportunity to talk to you about your business. All right, let's talk about heat pumps. Although we all know about them, not necessarily everyone is familiar with the technology behind the heat pumps. So I will spend a few minutes to give a brief information about common types of heat pumps. So how does a heat pump work? What is so special about them? Unlike traditional heating devices, heat pumps do not produce heat. Instead, they extract heat from a low temperature source, such as air, ground, or water, and turn it into a higher, more useful temperature for heating applications. Most of the heat pumps transfer heat by means of circulating a refrigerant fluid around a compression expansion cycle consisting of four main components. In the evaporator, which is a heat exchanger, heat is extracted from the outside source and boils the refrigerant. The gas is then compressed by a compressor, which increases its temperature and pressure. From the compressor, the gas is passed through the condenser, another heat exchanger, where it releases the heat energy to the heating system. This makes the gas cool down and condense to liquid form again. As the pressure is still high, the refrigerant is passed through an expansion valve before entering back to the evaporator, and the cycle is repeated. If cooling is required, then this process can be reversed. The overall operation requires some energy input, mainly to run the compressor. So how can we define the energy efficiency of a heat pump? The coefficient of performance, in short COP, is often used to describe the heat pump efficiency. The free heat extracted from outside plus the energy input used to run the system will give the total heat delivered. COP is calculated by dividing this useful heat output by energy input. So the greater the COP value, the less energy required to run a certain heat output, to achieve a certain heat output, meaning heat pump will be more energy efficient. Just to give you an example, let's say a heat pump system is delivering 12 kilowatt heat and COP is 4. This means the system will consume 3 kilowatt electricity when extracting 9 kilowatt free heat from the heat source to deliver 12 kilowatt useful heat. In other terms, this heat pump will be operating at 400% efficiency. So heat pumps can produce far more useful heat output than the energy input needed to drive the system. However, COP is not fixed for a given heat pump. This will depend on the operating conditions and temperatures. As you can see in this graph, the smaller the temperature difference between the heat source and heating temperature, the greater the energy efficiency of a heat pump system. In other words, heat pumps are more efficient when the heat source temperatures are higher and the heating temperatures are lower. So it's often more suitable to use seasonal performance, which is the ratio of total heat delivered from the heat pump to the total energy supplied to it over a year or a heating season. So what are the types of heat pumps? One of the most common configuration is air source heat pump, where the heat is extracted from the outside air. There are two main configurations of air source heat pump systems. In air-to-air systems, extracted heat is delivered to the building in the form of warm air using a fan system. Internal units are often wall-mounted and operate like a typical air conditioning system. They can be used for both space heating and cooling, but they can't provide hot water. If you want to heat more than one room using air-to-air heat pumps, the best practice will be to install on duct air heating system. For example, if a building that already has ducting but no radiators, then it is going to be less expensive to install on an air-to-air system. They are relatively low cost, but they are not eligible for renewable heat incentive scheme. If you haven't heard about it before, it's a financial support from UK's government to promote the use of renewable heat. Phil gives some information about this in his talk. Another type of air source heat pump is air-to-water systems, which is the common type for heating applications. These units transfer the heat from air into a wet heating system, which may include radiators, fan convectors, or underfloor heaters. As you can see, the water temperature will vary based on the heating system, and heat pump can be coupled with all these options. But as a rule of thumb, the lower the distribution temperature, the higher the efficiency of the heat pump will be. Air-to-water heat pumps are often designed for heating applications, but they can also provide cooling using fan coil units. They are relatively easy to install, can offer high energy savings, and they are eligible for renewable heat incentive scheme. There are some aspects to consider when siting the external unit for an air source heat pump. First is the spatial considerations. The external unit can be either mounted on an external wall or to be placed on the ground. As this unit has a fan that draws the outside air in across a heat exchanger, the good airflow is essential to interact effectively with ambient air. So it should be sited away from any potential obstructions. Otherwise, it will operate at lower efficiencies, resulting in greater energy cost. Another consideration is noise, mainly caused by the compressor and fan. This is often in the range of 40 to 60 decibels, depending on the product. Also, the larger the system, the noisier it will be because it will need more air circulation. So they need to be positioned carefully such that they do not impose noise on the neighbors. They also should not be located next to bedrooms or on floors that can transmit vibration. As long as good quality products are used and installed according to manufacturer's instructions and the microgeneration certification scheme planning standards, they will operate efficiently with least destruction. They require regular maintenance, but often operates for 20 to 25 years if installed and maintained properly. Another common type of heat pump is ground source heat pump, where the heat is extracted from relatively stable temperature of the ground or groundwater and then transferred to or from the heat pump refrigerant cycle via heat exchanger. Most of the ground source heat pumps are a closed loop system, where often a water antifreeze mixture is circulated through the sealed pipes laid horizontally or vertically in the ground. In the horizontal systems, the collectors are typically buried in 1 to 2 meter deep trenches and require relatively large ground areas free from hard rocks or large boulders. They come in different forms, could be straight pipes with single or mountable pipes, or coiled pipes positioned either vertically in a narrow trench or laid flat horizontally at the bottom of a wider trench. The type of trench configuration depends on the land availability, ground properties, or the choice of installers. Alternatively, heat can be extracted through vertical closed-loop collectors, where a borehole is drilled into the ground, typically 20 to 120 meter deep, although it could go down to 250 meter, and the change of the depth and the number of the boreholes often amounts the same thing, and the choice is often a matter of cost and practicality. And these systems often offer higher thermal efficiencies and require less pipe and pumping energy. They are also less intrusive to install compared to horizontal configurations. However, they are more expensive, mainly due to the higher cost of vertical drilling. Heat can also be extracted from groundwater or surface water using an open or closed loop system. In open loop systems, water is directly pumped from an underground or surface water to the heat pump and then returned back to the water resource. These systems can offer a cost-effective solution as they require relatively inexpensive wells with a small ground area. They can also use cooling effect of groundwater without running a heat pump in the summer. However, water availability is often limited and the output depends on how much water that can be extracted. In addition, fouling and corrosion may cause problems depending on the water quality, so more maintenance may be required. Also, there are restrictions in using groundwater. So closed-loop system is most likely to be more practical. Like the trenches, a secondary fluid is circulated through the collector pipes, which can be safely secured to the bottom of a lake or pond. The temperatures at the bottom of the lake are likely to be similar to those of a good trench system. This can be an excellent proposition if a lake or pond is available, as it will avoid the cost of digging trenches or boreholes. But a great consideration will be required to ensure that the collector pipes will not damage. Just to summarize, ground source heat pumps take the advantage of stable ground temperature throughout the year, and this allows the heat pump to operate close to its optimum design temperature, optimum design point. So they offer greater overall efficiencies than air source heat pumps and are less likely to need alternative backup heating. In general, they offer the greatest energy savings of all heat pump types. They're also highly reliable as they have less moving parts and they're not exposed to weather, so maintenance costs will be low. Once installed, the system is non-intrusive, so the collectors, because collectors are buried out of sight. They can also offer long life expectancy, typically 20 to 25 years for the heat pump and up to 100 years for the ground collectors. However, they are limited by the land availability and often more expensive to install due to the current high cost of the groundwork. Installations could be disruptive and complicated, especially in dense urban areas. Optimum solution for a site will depend on the location, heating requirement, and land or water source availability. Also, you need to consider the space to dig trenches or access for drilling equipment. For ground applications, the design of heat pump highly depends on the ground properties, as the composition of the ground affects its heat capacity and thermal conductivity. So knowledge of the ground thermal properties can help avoid undersizing or oversizing of the ground collectors. There are also exhaust air heat pumps, which can extract heat from the warm inside air as it leaves the building via ventilation system, and then transfer the heat to the supply air, hot water, and or a heating system. These systems operate with a mechanical ventilation, which also can help improve the indoor air quality and prevent condensation. They don't require an outdoor unit, and since the inside air temperature is approximately 20 to 22 degrees C all year around, the maximum heat output does not change with the outdoor temperature. They're often suitable for new builds or when developing new apartments, and they're most cost efficient for small to medium homes. Heat output is limited by the exhaust airflow rate, so may not match the heat demands, and a secondary heater may be required. They provide energy savings, but they're not eligible for RHI. Right, there are so much to talk about heat pump technologies. Today I just wanted to give a very brief overview of most common types. But before finishing my talk, I want to point out a few considerations. So before considering any heat pump, it's really important to minimize the heating demand first. This means the building is well insulated and airtight, and there are efficient heating control systems. Whether this is at the building design stage or for retrofit exercise. As we saw earlier, the lower the heating temperature, the greater the efficiency of any heat pump. So underfloor heating is definitely something to consider if it is practical and possible to install. Although heat pumps can also be used for cooling, it's best to avoid the cooling requirement at the first place, perhaps through some passive measures such as window blinds or external shades. A range of heat pump solutions is available, with each option having its own merits and specific requirements. So the site surveys are really important in order to identify the optimum solution for a particular project. Heat pump performance can be significantly compromised by incorrect specifications and sizing, poor installation, incorrect commissioning, and incorrect operation. So it is essential to go with a professional installer qualified by microgeneration certification scheme, and ideally with a track record and successful case studies. Finally, energy meters should be installed to monitor how much electricity has been used and how much heat has been generated. This will allow the installation to be fine-tuned, if you like, which can help adjust the operation of the system to improve the overall performance. Thank you very much for listening to me. Now I'm going to hand it over to Seamus.
Thank you very much, Gulcan. And I hope I'm going to be sharing my screen. Can somebody confirm that they can hear me, please?
Yes.
Excellent. And can you see my screen?
Yes.
Tremendous. Thanks very much. So I'm going to march through a set of slides. My presentation is called Heat Pumping and the Net Zero UK. I'm a professor of mechanical engineering, specializing in dynamics actually, at the university. I've got a particular interest in achieving a 100% renewables powered world. Let's start with the UK. And especially discovering the role that energy storage will play in that. So my angle on this is very much from the perspective of how are we going to achieve a 100% renewables powered UK, and how are we going to do that before 2050? And I'll start with a little warning. This is an academic talking, so academics like to talk about general principles, understanding things from a high level, particularly talking about future directions. So what I'm going to focus on today is not what you can buy in B&Q. It's what you should be able to buy in 10 or 15 years time, arguably 10 years time, let's hope. So I don't profess any particular direct expertise of what's on the market at present in terms of heat pump offerings. I would say my command of thermodynamics is very good, so I do fully understand the idea of coefficient of performance increasing and decreasing depending on the temperature range, and that's one of the important points that's going to come out in what I'm saying. So let me start off by saying, or trying to persuade you, that the cheapest energy that we can now get, the cheapest electricity that we now can get, is from renewables. And an enlightened perspective of what our energy system of the future will look like is one where the cost of just generating electricity, will not be the major system cost. Now, here's an example. Onshore wind is costing significantly less than £50 per megawatt hour. And we are paying more than that on average, or about that on average, for our electricity generation in the UK. And that's going down. That's still going down. And what will happen in the future is, for all practical purposes, the enlightened view of how much it costs to generate electricity will be it's very close to zero, and that the real system costs are actually elsewhere in the system. Now, I know that's a controversial view. I'm sure some people will challenge me on it, and please do. I'll be happy to defend that. Here's a little report from September last year, which just shows the extraordinary progress that has been made in offshore wind. In September 20th last year, we had an award of a contract to a consortium comprising SSE and Equinor, who promised that for a big new wind farm that will start delivering electricity in 2023, they will produce that electricity for less than £40 per megawatt hour. Now, even coal-fired power stations don't do that. So offshore wind was predicted back in about 2010. It was estimated to be about 130, 140 pounds per megawatt hour. And back in 2012, there was work done to see if we could bring it below 100 pounds per megawatt hour by the end of the decade, 2020. And here we are smashing those ambitions by making extraordinary progress, and it's still going down. So you will see offshore wind prices come down to possibly 30, possibly below 30 pounds per megawatt hour in the next decade, significantly cheaper than anything else. And and the real star of all renewable energy, although not one that a mechanical engineer can do much with, is PV. And the picture on the right is drawn from the URL that you see here. which announces an auction in Portugal that returned, I think it was €14.60 per megawatt hour. So this was for PV generated in Portugal. And the image on the right is drawn from a magazine called Electrek, which plots the best price per megawatt hour in dollars per megawatt hour versus the year. And if you look at this curve, you'd be forgiven for saying, well, it looks like a straight line that's going to cut through zero in about 2020. Well, it hasn't quite done that, but it's achieved enormous reductions in cost, and it will carry on. So for PV particularly, there's almost no limit, no lower limit to how inexpensive energy will be. And this graph is what I think is the key truth about future energy systems, is that as we have low penetrations of low carbon generation, so on the bottom axis here, the x-axis, you've got the penetration of low carbon generation like wind turbines and photovoltaic panels. As that is fairly low, most of the cost of producing electricity is actually just generating it. But as that penetration gets higher, we'll spend relatively little on producing the electricity and relatively more on delivering it at the right time. Now, that's an important point. Flexibility, which is what I'm referring to here in general terms, the ability to deliver electricity when it's useful, is going to be more valuable than just generating the electricity itself. And you might say, well, where does all this relate to heat then, and how does it relate to heat pumps? The big game in the UK is heating. This is a graph that's appeared in a number of different formats, all produced by Grant Wilson from Birmingham, which illustrates the point very clearly. There are a few different curves on this graph, but I just want to direct your eye to two of them. The red curve that's hovering about 1,000 gigawatt hours per day, or about between 800 and 1,000, is electricity usage currently per day. So from years 2015 up to 2018. So that we're less than 1,000 gigawatt hours per day in there. And the blue curve above it is what we're using in gas every day. And most of that gas, the vast majority of that gas, is used for heating up our houses. So you see that we're going above 4,000 gigawatt hours on certain occasions. This spike in about March 2018, the highest spike on the graph was the beast from the east. And it's when we burned a lot of gas because there was a lot of snow outside. People were at home because of the snow, and it was very cold, so they turned on their heating. So the big point about this graph is heating is consuming a lot more energy than we're using currently in electricity. And Gulcan mentioned earlier on the idea of a coefficient of performance. If we were to supply all of that heating from heat pumps that had a coefficient of performance of 4, let's say, then we could reduce the peak electricity output required for the heating from about 4 terawatt hours, 4,000 gigawatt hours per day, down to something like we're currently using. So in other words, we'd almost double the the electricity generation capacity that we currently need. And I would like to see us do that. So heating matters a lot. At the moment, we're releasing 60 million tons of CO2, burning gas for heating. And if you just set that in the context of our ambitions, well, our ambitions are now net zero by 2050, but they were until June last year. They were an 80% reduction relative to 1990 levels. So leaving 20% of 820 megatons would be leaving 160, is it? Yeah, 160 megatons, of which heating is already chewing up 60 out of our target of 160. So the key point here is that we have to do something big about heating in order to achieve net zero. And for most people, there are two main options now. There's the first option, which is we could transmit hydrogen in the gas network. And that is a direction of travel that's gathering a huge amount of pace. So almost, in my view, without sufficient thought, it's a possibility, but people are almost assuming right now that that is the solution. And the alternative solution, the main alternative, is that we use heat pumps. And I'm in favor of us keeping an open mind. And the main reason why I'm motivated to give this talk is I want us to remain open to the idea we don't necessarily have to transform our gas network over to hydrogen. We can, and in my view, should mainly be heating properties using heat pumps. Here are some statements, attributes of those two systems. In both cases, it's true that large amounts of energy can be stored efficiently as hydrogen. So I do think we will make a lot of hydrogen in the future, irrespective of whether we do our heating with electricity or hydrogen. It doesn't particularly play to either one of those sides. The second point is a really big one. If you go electricity, make hydrogen, and then make heat, you'll only get about 20%, about a fifth as much heat as you would have done had you simply gone electricity to heat with heat pumping. And the reason is that making hydrogen is about typically 70% efficient with a very good electrolyzer, and then you'll get 100% of the heat value out of the hydrogen. So you get 70% of 100%, which is 0.7. Whereas with heat pumping, you're very likely to get 3.5 or 4 as an average coefficient of performance. Electrolyzers are relatively expensive. They're more expensive per kilowatt of capacity than wind turbines. So if you buy a 1 megawatt wind turbine onshore, it's about $1 million. An electrolyzer is more like $2 million per megawatt. On the downside, well, people say anecdotally heat pumps are expensive. I put a question mark around that because in my view, what they cost today is not an indication of what they will cost in the future. And this next point is one I'm going to focus on for almost the rest of the talk. Air source heat pumps are excellent most of the year, but they perform relatively poorly in cold conditions because you're trying to take heat from very cold air and pump it up over a big temperature difference, and there are potential problems with freezing of ice onto those. I'm sure Phil will say more about that in due course. So I want to make basically an emphasis on those 2 points. Making heat from electricity is much better done via heat pumps rather than turning it through hydrogen. There's a factor of 5 difference between the two. And there's a potential issue in the future about heat pumps in very cold conditions if they're air sourced. So just a little calibration. If we use 4 terawatt hours, that's what I spoke about previously, on a cold winter's day to heat 25 million homes, that's about 160 kilowatt hours per home. It's a lot of energy per home. I'd like us to think about storing 100 kilowatt hours of heat using water, say between 35 and 95, and that would need about 1.5 tons of water. That's actually very compact and is very cheap. And if you think about trying to do the same, sorry, go back a line. I think you could probably do that for $100 for the tank. It's basically a plastic tank with lagging on it. I think to do the same thing with batteries would cost you more than $20,000 just for the cells. So I want to tell you about a concept. This is the main thing in my mind in making this presentation. And this concept was inspired by a talk that I heard in Birmingham in August of last year by Professor Jiping Feng of Guangzhou Institute of Energy Conversion. And he basically talked about using the latent heat in ice slurry. Effectively, what he's saying is take in water, turn it into ice, throw away the ice, and you have extracted heat from water, quite a lot of heat from the water, and you can use that as your cold source. And I've married that together with a concept of my own, which says that you could take in non-drinking water through existing and soon to be redundant gas network, and that could serve as the mainstay of our low temperature heat for heat pumping. So latent heat pumping is all about freezing water and using the extracted heat. The amount of heat you get out of water by freezing it is 334 kilojoules per kilogram. It's the same amount of heat that you would get out of water if you cooled it down from 80 degrees C to 0. So it's a monstrous amount of heat, 334 kilojoules per kilogram. If you were using latent heat pumping, it has a relatively high coefficient of performance because the temperature of the cold source is 0 degrees all the time at worst. So that would require about 1,300 kilograms of water, about 1.3 tons of water on the coldest day of the year. This is a little animation, a little video that Professor Jiping Feng did. I'm just going to play it. I hope it shows up over Teams, but it shows somebody pouring a liquid out of a bottle, and that liquid starts to turn into an ice slurry in a glass bowl. And what you see is it looks like water coming in. In fact, it is water, but it's water at -2 degrees Celsius, and it's spontaneously turning into what you would probably know better as a slush puppy without the flavoring in it. Okay, this is a system diagram for a so-called abandoned water system, where you take water from a source. In Professor Feng's case, it's taken from a river or a lake, and you use that to supply latent heat. It has been applied in China, and it's very successful in this 25,000 square meter building in Nanjing province. And here's some images for the inside parts of that system. So I'm going slightly fast. I'm conscious I'm closing to my 20 minutes slot. My point here is it's real, it exists. Professor Feng has built this and several times over, and they've just won a new research award, and we hope to work with them in pushing this forward. Professor Feng has done some studies showing how the coefficient of performance varies across different locations in China. And if we focus on the cold places, like Harbin gets very cold, being quite far north in China, and Beijing gets fairly cold, with a water temperature in just above freezing, he's still getting a coefficient of performance with his heat pump of more than 4. So we can count on a coefficient of performance of 4, even in the coldest times. So my conjecture is we should drive not drinking water, non-potable water, through the existing gas network and use this for the combined purposes of providing the low temperature heat source for heat pumping, and by the way, also for flushing toilets. So let's do a little check on that. If we wanted to provide 120 kilowatt hours per day of heat, I said already, it's 1.3 tons per day. You would only need that on the very coldest day. It's an average flow rate of 15 milliliters per second. It's tiny. And in an average bore of 20 millimeter pipe, it's much, much slower than walking pace. So it's very, very easy to push this much water through the existing gas network. Pressure is no problem. Flushing toilets is not an insignificant issue. 32% of our water consumption in the UK goes down toilets, and that is drinking quality water. It's pretty shameful. And 1% of our greenhouse gas emissions are from treating wastewater. So there's already a little win just by saying, let's flush our toilets with a different water than drinking water. Could you get rid of the ice slurry? No problem. Pour it down the drain. The drainage system won't freeze. In fact, the drainage system is becoming a ground source heat pump for you. If you look at the electrical power effects, if you have a coefficient of performance of 4, you need 40 kilowatt hours of electricity, which would be about 1.7 kilowatts on average in the coldest day of the year. And finally, water shortages is an issue some people come up with. Well, we have them in summer. We don't ever have them during the coldest time of the year. So the key issue underneath all this is, well, we shouldn't be thinking of using heat pumps in the same way as gas-fired generation. This image on the right-hand side was given in a lecture at Nottingham on the 2nd of April. and it was Grant Wilson who produced the chart earlier on, shows us that gas heating does something extraordinary. It varies by 120 gigawatts over a period of 3 hours in the morning. And even if we heat pumped with that, we'd still be talking about a rise of 30 gigawatts in 3 hours every morning. And the electricity system couldn't cope with that. So I'm proposing we do something different. I'm essentially proposing that we would have a warm water tank within a house, which would keep water at a lower temperature at 25 degrees and at an upper temperature at 40 degrees, and that could be used to help us to smooth our way through varying heating demand through the day. Okay, because of time, I'm just going to conclude now. So these are my closing remarks. Decarbonising heating, first of all, is an absolute must for future UK power systems. Gulshan is exactly right that our first priority in that is improving insulation. So let's reduce the amount of heat that we use. But then after you've done that, I see two main classes of solution, using heat pumps or using hydrogen. And I think that there's a bit of a runaway train towards the hydrogen solution, which needs to be rethought a little bit. I personally think heat pumping has a huge role to play. I recommend that we think about using non-potable water as a low temperature heat source for latent heat pumping, and that we could get this through our existing gas network. And if we do that, there are strong benefits for short-term energy storage of up to 10 hours, which will help us hugely with the integration of renewables. Thanks very much. I'll hand back to Gulshan, I think.
Thanks, Seamus. Now I think we will hand it over to Phil.
Yes, can everybody hear me?
Yes.
Yes.
Right,
Yes,
I'll share my presentation. Can we see that?
Yes.
Great. Well, good morning, everybody. Thank you for listening today and following on from those fantastic presentations. So hopefully I can keep up the pace here. Lot of discussion points in those. Really excited to listen to those. So Gulshan mentioned how heat pump works. Seamus obviously looked at what challenges we've got in decarbonising heat, as heat from buildings and our homes are one of the largest challenges, as well as transport. So the government's committed to net zero. So how are we going to actually require net zero by 2050? And really at the moment, there's only heat pumps to actually achieve that. Okay, Seamus mentioned hydrogen there. Hydrogen may be a solution, but when? Okay, and the issue today is we can't wait for something which may come up in the future. And at the moment, heat pump is the only solution for achieving carbon reduction and reduction of heat in our home. So that's what I really want to discuss today. Quite a lot of few slides, so I want to rush through them. And if I've got time at the end, it's just to go for some case studies to show you where heat pumps are used in buildings and homes today in the UK. So I just want to do a little introduction. Delivering net zero. The government's committed to net zero by 2050, and what is required for heat pumps to gain market penetration to achieve net zero. I'll outline the heat pump industry's readiness to step up to that challenge and deliver decarbonisation of heat. Heat pumps offer a huge opportunity for immediate carbon reductions and carbon savings compared to traditional heat systems. And with the efforts of industry striving to deliver these benefits alongside supported and proven policy mix, heat pumps can scale to play a vital role in decarbonisation of heat. So why heat pumps? So Seamus discussed about how in the last 10 years we've seen a massive reduction in the decarbonisation of electrical generation. So heat pumps now around about 0.08 carbon intensity compared to oil, LPG, natural gas, which are probably 80% 80 to 90% of homes at the moment. Very high fossil fuel carbon producing products. So by reducing to heat pumps offer a huge carbon saving, around about 65% compared to gas boilers. But it doesn't stop there, because as Seamus mentioned, that will continue. The reduction in carbon emissions from electricity will continue in the next 10, 20, 30, 40 years as we go towards 2050. So a heat pump installed today will continue to reduce carbon over time as the grid decarbonizes at the same time. That can't happen with a gas or oil boiler. So we're projecting in around about 2050 that a heat pump will be around about 0.01, which is incredible, really. So that would be around about 95% reduction by 2050. So you can see why heat pumps are one of the solutions now to reduce carbon. So the scale of the challenge, it's massive. Okay. Seamus said there we've got 25, 26 million homes. 80% of those homes are gas. So the challenge is immense. Okay, and the Committee on Climate Change recommends that by 2050, that 19 million heat pumps should be installed, and over 1 million installations per year by the mid 2030s in order to meet net zero. So the challenge is immense. Okay. So this represents a huge scaling up compared to current levels. So if we look at 2019, around about just under 30,000 heat pumps installed. I mean, that's minuscule when we compare that to gas boilers. In the UK, we install around about 1.6 million gas boilers a year. Okay, it's immense. So the challenge is immense. So this is the type of installations, heat pump installations, we can see on this graph that we've got to achieve by 2035 to some way get into the carbon reduction which is required. So it's a massive uptake. Where will that come from initially? It will come from new build. Okay, we've got a new building regulation set to come in at the end of this year, beginning of next year. Consultations just gone through. And we're looking for a reduction in carbon emissions from new homes by better insulation. That will drive heat pumps, because obviously gas boilers will maybe have to do additional things to the building which they won't be able to achieve. So heat pumps naturally will be a solution. But by 2025, the government's already committed to the Future Home Standard. So that will mean that it would be very, very difficult when that standard comes in to actually install any fossil fuel boilers in buildings. So that's when heat pumps become a massive solution. And then the challenges after that is how we're going to retrofit the existing homes. So there has to be a combined retrofit solution of energy efficiency on existing homes, together with decarbonisation of heat in homes. So the challenge going forward from 2025 to 2030 and then 2030 to 2025 will be refurbishment of homes. So how do we compare to other countries? Well, not very well. If you look at this slide on other European countries, okay, and this is the number of heat pumps per 1,000 households. Norway at the moment is the larger installer of heat pumps. They've done quite a lot of policy changes to reduce fossil fuels. They're actually one of the first European countries to actually ban oil. Okay, so you can't actually replace a oil boiler with another oil boiler from 2020. They've been very good with incentives, regarding cash incentives for people to swap over from fossil fuels to heat pumps, and we've seen the success of that. Sweden, company I work for, NIBE, has been manufacturing heat pumps since 1979, and 90% of all new homes built in Sweden now will have a heat pump installed with it. So Sweden for 20 years or so has been one of the major countries with heat pump installations, but that is also the rest of Scandinavia. So Finland, Estonia, Denmark, Switzerland, Austria, France, Italy. So a lot of those countries there, which are installing thousands of heat pumps a year, are very cold countries, designing down to -25 in the depths of winter. So modern heat pumps are designed to work in Nordic conditions, compared to the UK, where we design to a worse heat loss on the coldest day of -3. So we live in quite a temperate country. So heat pumps are ideal for our type of climate. So we've got some key lessons to learn from those countries about increasing deployment of heat pumps. So policy is one. Okay, so if we have some examples of that, France has got the France Quality ERN promote quality installations. So industry support for certification of skills. Sweden got different eco labels, P label, quality mark, installer standards, driving installer standards. If we look at Finland, was one of the first countries to adopt a carbon tax from 1990. So taxation is another example of policy. Planning policy, Belgium requires a net zero requirement of less than 15 kilowatt hours per meter per year. So planning, if you're doing retrofit and new build properties, and upfront financial incentives, as I mentioned in Norway, but that's also happening in the Netherlands. And Netherlands is probably one of the closest countries to the UK in Europe because of the reliance on North Sea gas. So they're producing grants of 1,100 and then £100 per kilowatt. So there's some lessons to be learned in the rest of Europe. So with these lessons in mind, we've really developing a heat pump market will come with three key areas. So we've got industry efforts, government support, and consumer acceptability. So if we go into industry efforts, so we saw in the early slide, basically training enough installers. At the moment, there's less than 1,000 installers qualified to actually install heat pumps, and that's compared to around about over 130,000 gas installers. So the challenge to actually upskill those installers is probably the biggest challenge we've got. So heat pump manufacturers already provide training for installation of our products. We need to expand that further to ensure there is enough installers to meet the rising demand, and installers will come through upskilling, and it's the upskilling of the current installer, okay, and then apprenticeships for new installers coming forward, because the skills to install a heat pump and not that dissimilar for the skills to install a gas boiler. They're installing a heat source, and then the radiators and the pipe work are exactly the same. So the core skills are there. It's more around the design of the system and how to install a heat pump. So, as I say, increasing the skills is a key area. So boiler installations which are going now, the vast majority of gas boilers are gas condensing combination boilers. So as I said, 1.6 million. So these boilers are being installed, but are not typically optimized to get the most out of that technology. Okay, so meaning that not necessarily they're getting the best fuel bills for consumers. Installation heat pumps are more sensitive. They require often not be carried out different, as I said before, from typical heating systems. Okay, we have to do hydraulic balancing. We have to be very careful of heat loss and flow temperature calculations with heat pumps. So we need to have a training program which must feed into a skills card. So that's what we're lobbying government to have a skill card, and to help upskill of installers, to provide a guarantee of quality for installers. So consumers feel confident that they're getting their system installed, because if we don't control that, then consumers are going to suffer. So meeting the manufacturing demand, this is always one that comes out with heat pumps. You saw the 1.6 million gas boilers, but only 20,000, 30,000 in the UK. But you saw the amount of heat pumps. There's well over 1 million heat pumps currently being installed in Europe, and that's growing every year. Many heat pump manufacturers like NIBE are large multinational companies with capabilities and capacity to scale up production. If you look at air source heat pumps, they're basically an air conditioning unit, okay, very similar production. And air conditioning in the world is over 141 million units worldwide, okay, and many of those units were supplied by companies who are actually heat pump manufacturers. So actually manufacturing these units is not an issue. So with clear commitment from government and extra investments, ramping up manufacturers will stimulate investment. So the next one is government support. So the government policy is vital. So it's vital to give the right signals needed to demonstrate there's a firm direction for heat carbonisation. And in particular, heat pumps make immediate sense in new build and off-grid homes. They're the low-hanging fruit. So policy to develop heat pumps in these sectors will set the deployment of heat pumps on a growth path to mass market. And that hopefully will already happen with the new building regulations and the future home standard set for 2025. So some of the things we're asking for in the building regulations, which look like they're already going to be in there, is setting a maximum of 55 degrees for new build especially, but also retrofit, because that would mean if we're putting a gas boiler in now, you're making that heating system heat pump ready when you want to swap out that boiler in the future. Delivery of future home standards, as I mentioned. One of the biggest areas is freezing the loophole for house builders in building regulations, because house builders, if they put foundations in, they can keep those building regulations forever, basically. So we've got 40% of sites being built last year, homes were pre-2011 building regs, which is crazy. We should be building homes now. We don't need to refurbish in years to come. We've got a biggest enough challenge with the existing homes we've got now. So we need to tighten our energy efficiency requirements. So we need 31% reduction on the current levels of 2020 building regs, ensure sufficient electricity connections, hot water cylinder requirement, and reverse the permitted volume for outdoor units. So carbon standards and regulation. So a clear line needs to be drawn to guarantee the decarbonization of heat, and this can come through emission standards for heat replacements. So we're mandating 221 grams per kilowatt CO2 per kilowatt by January 1st, 2025, reducing that to 170 by 2030 and down to 110 by 2035. And then mention the RHI. RHI actually finishes in 2021, and we've managed to convince the government to replace that with an upfront scheme, which will take us up to 2025. So we feel an upfront grant is the best approach, which will appeal to customers, because at the moment the RHI is attractive, but you get that money back on your initial investment over 7 years. So if you haven't got the money in the first instance, then it's a non-starter. So offering an upfront assistance to the consumer is more attractive to the consumer. And rebalancing taxes. Okay, taxation should be rebalanced to reflect the carbon content of fuels. So what we're recommending this slide is a total carbon price for electricity and the total carbon price for gas. Okay, and the operational cost of heat pumps would fall below gas boilers as a result. There has been talk of that in budgets, and we have to be careful because we could drive We don't want to drive existing homeowners into fuel poverty if they see their bills go up, but there has to be a clear direction of travel of how we're going to reduce carbon. And carbon taxes is one area if done correctly. And the technological limited. So we've talked about consumer acceptability. So consumer demand is crucial for heat pumps. I think a lot of consumers now are aware of the need for reducing carbon. They're aware of the climate emergency, but not so knowledgeable about heat pumps. But electrification is happening, and it's the technological familiarity of the actual product. So industry needs to recognise the importance of installers. They are the key salespeople for low heating solutions. They're the people who go into homes every day and are selling the actual heating system, and that's what who the consumer listens to and trusts. So we're ready to step up and deliver a skilled and knowledgeable installer base that can ensure both high quality installation and consumers, and share that knowledge with consumers to get the best heating system and reducing carbon in the homes. So heating manufacturers, we're at the leading edge of innovation in heating system design. With these costs continue to be made, cost down will continue through installation costs. So we will see installation costs of heat pumps reduce as more heat pumps get installed. We need a reliable demand and increased familiarity with the process. Government spending can help in providing an initial boost through upfront grants and set us on a growth pathway. And really, heat pumps have the potential to revolutionise the way heat is consumed. So the use of smart controls, as Seamus with thermal storage with heat pumps, offer exciting innovations such as heat as a service. Okay, so you don't pay for a heat pump, you rent the heat pump. Dynamic pricing and Internet of Things. Manufacturers will continue to keep innovating and enhancing the product as we offer, because the heat pumps today will be totally different by 2035. So we're ready to step up, and so with the efforts alongside proven policy of mix and support, HPI are confident the heat pump market can grow and create decarbonation of heat. So I know I'm stuck for time. I just wanted to show you 2 minutes on some case studies. So when we talk about heat pumps, people always say about, they can only be used in new homes or highly insulated homes, and people think of a house like that straight away. Grand Designs, you see them on Grand Designs, and yes, heat pumps are installed in properties like that. They're ideal. People who build a home house or self-build, they're looking for innovative products, and heat pumps is one of the products. Air source in those type of properties as well. That's again a new build installation, very modern. But they're also used in standard new builds now, built to current standards. So heat pumps are gaining, especially gaining prominence in new build, especially in off-grid areas. But also can be used in older properties. This house built in the 1700s. You'd have people say heat pumps can't be used in hard to treat homes. Heat pumps can't be used in old properties. Heat pumps can only be used in eco homes. Quite clearly, it shows that a correctly designed heat pump can be used in any property. Another house, thatched cottage in Cambridgeshire, again has an air source heat pump. But not only that, it can be used in commercial. This is a air source used on a care home property. And also in commercial premises. These are heat pumps used in a commercial application in warehousing in Teesside. So heat pumps have applications in every sector of our buildings and can be used for heating, for cooling, for hot water, and also apartments. Okay, apartments, 20%, 30% of new homes built for apartments. I can mention about exhauster used in small properties, using the air we waste from ventilation to heat and hot water. So ideal for apartments as well. So that's my presentation over. Thank you again for listening. I'm sorry if I slightly went over.
Thank you very much, Phil. Thank you to both our speakers for their very interesting talks. So we have a few minutes for questions. If you want to pop them in the chat box, so we still have time for this. And just looking at the questions, actually, your talks already addressed a few of them, but one of the questions was, would a heat pump work well for a listed building that cannot be fully insulated? Phil, I think you already say that it is possible and it will work fine.
Yeah, again, it has to be designed correctly. We've used heat pumps in stately homes, in old buildings. Yeah, it has to be designed correctly. You need to try and do as much insulation as possible. Obviously, in older buildings, if it may not be possible, but if you can try and do it as the minimum requirements, and that is always helpful. Yeah,
absolutely. Okay, thank you. Charlie asked about using wax as the phase change material. And that's, I think, referring to thermal energy storage that Seamus mentioned. Seamus, would you like to make a comment on that?
Very briefly, as I said in the chat, I think it's a very good idea. I cited water as a possible thermal storage medium simply because it's extremely cheap. And in fact, because it has such a high specific heat capacity, it's actually not a problem to do it with water. But wax, particularly built into the fabric of a building, is one of those directions of travel for future buildings that is very exciting and adds a lot of value. Yep, good point.
Yeah, absolutely. Brilliant. Thank you. Andrian asked about likely reduction in the heat pump installation cost and what our view on the likely trend and government policy instrument needed to bring this about. I believe, Phil, your talk has already answered this question, but is there anything else you wanted to add?
I think as economies of scale, I mean, people cite about heat pumps getting down to the price of gas boilers. That won't happen because we see in countries which heat pumps are well established, heat pumps are always going to be more expensive than traditional fossil fuel boilers because of the type of products in it. But obviously economies of scale will drive down that cost. But it's more in the installation costs as well. As I said, there's 130,000 gas installers and only 1,000 heat pump installers now. Competition will drive costs down as well.
Absolutely. Okay, thank you very much. Another question from Martin. Is it realistic to provide an air source heat pump system for a very energy efficient new build that provides sufficient hot water and space heating, but without a storage tank?
Well, you'd need a hot water storage, and that is one of the biggest challenges for heat pumps, especially in retrofit, because a lot of gas boilers which have been installed are combination boilers, which is instantaneous hot water, and people have taken hot water tanks out. So currently there isn't the technology where it's instant water. I'm not saying that could not happen in the future, but at the moment, if you install the heat pump, you would need a hot water cylinder. Unless you had a hybrid system and kept the boiler just for hot water and the coldest days and the heat pump for the heating, that could be a solution, but that would probably be more of a temporary solution.
Okay, brilliant. Thank you very much, Phil. Another question from Neil. Roughly, what is the cost for a ground source heat pump for a standard 3-bed terraced house, including design, material, and installation, assuming the property has good insulation?
It's always a tough one, so don't hold me to it. I would say that installation on that type, depending on what's required, you'd be talking between £15,000 and £21,000 on average.
Right. I have a question, Phil. Let's say the cost and the land availability is not an issue. Is there a preference between the horizontal and vertical systems?
They work just the same. with a ground system tends to be the most favoured, because most people who are putting ground source now have got land availability. But if we're talking mass market, then drilling would be the ideal solution, because people generally, you won't be able to put the ground loops in your existing garden. What we're trying to recommend, and this is an area where ground source needs to be separated, because the cost of a ground source and a source actually installing it in a house is exactly the same. The only additional cost is ground cost for the work. What we're trying to say to people is, with ground source, you've got an opportunity to separate that and make the ground arrays part of the infrastructure, shared ground loops. So we could go mass ground loops within urban conditions or on new build estates, where the homeowner then just pays a standing charge. And then you will get investment, because it's a low risk, low regret investment. Once you put in ground loops or boreholes, they're there for 100 years. The investment is incredible. Okay, it just needs the incentive to actually somebody to invest in that, and that you will only have the increase in ground source heat pumps through that. But the benefit of that is that then we've got the ability for free cooling. And if we're going to have, as they say, we're going to have a warmer climate in years to come, then free cooling could be a massive benefit.
Absolutely. Yeah. Thank you very much, Phil. Very nice. Is there any more questions that are coming? We have a couple of minutes if you want to ask a question. I have a question, but of course it depends on a particular project. But if you have a cooling requirement and you can't avoid it, what could be the ideal solution for heating and cooling, providing both heating and cooling through heat pumps?
Was that one for me, or was that for Seamus?
Yes, Phil.
Okay. Well, as I said there, with ground source, if you've got a borehole, then the temperature of the water coming up is around about between 6 and 9 degrees, and that's ideal for passive cooling. Okay, with an air source, then you can cool, but you're going into reverse, so you're actually reversing the cycle of the heat pump, which is obviously costing is a cost, because you're driving the heat pump. Where a ground and most offices are cooled that way. It's no different. They're cooled through an air conditioning unit, and it's exactly the same principle that with fan coils. Where ground source has an advantage in the cost effective is that you could use the ground as free passive cooling. Design is important in that. If you've got buildings with high solar gain, or you've got cooling for industry, then you may not be able to get down to the temperature required, and so then you would probably have to go into active cooling.
Okay. Martin has a follow-up question on air source heat pump related question. He's asking, what could we have a ground source heat pump solution that uses? Could we have a ground source heat pump solution that uses a single loop for multiple houses, but allows us to build households individually and therefore claim RHI to cover the cost?
That can be done at the moment through non-domestic RHI. Through shared ground loops. Unfortunately, domestic RHI finishes next March, and there is no successor for that. So this is one of the areas where we're trying to promote is looking at it as an infrastructure, and I think that is the only way mass market for ground source will happen, by shared ground loops and infrastructure.
Okay. Paul has a question to you, Phil. He's asking, can you cool via radiators? If so, are there condensation issues on the panels?
Yeah, you couldn't go through the radiators. You'd have to either have separate it and either use underfloor cooling or send it through fan coil. So you'd have some sort of diverter valve which would switch between the radiators to a secondary form of cooling. There is certain radiators which work more fan coil type radiators, which can work on heating and cooling. But they're more, I would say, commercial application. There's not so many which look pretty in a home. But condensation is an issue. So if you're doing underfloor cooling, then you have to make sure that the temperature of a slab is no less than 15 degrees, or else you'll get condensation forming on the floor, which you don't want.
Okay, thank you very much, Phil. I think I'm going to stop here. But we can, well, if you have more questions, of course, we will be happy to address them later. So I want to say thank you very much to our speakers for their contributions. And just wanted to share my screen at the same time. Right, so thank you very much for our speakers for your contributions and sharing their interesting insight with us today. I also want to thanks to our marketing officer, Michelle Patterson, for their great efforts to run this webinar smoothly. And finally, thanks everyone for tuning in for our webinar today. I hope you find it interesting. If you have more questions about the topics raised today or about energy innovation and collaboration, energy for business support, and any collaboration opportunities with the University of Nottingham, please don't hesitate to contact us. We will organize more webinars in the energy-related topics. So if you want to hear from us, please sign up for our energy newsletter if you haven't done so already. You will receive a very short survey link for a very short survey about this webinar. We would greatly appreciate your feedback if you have a couple of minutes to fill this form. This will help us share our future events. Well, we hope to see you again. Have a wonderful day and enjoy the sunshine. Bye.